here like to draw? You like to draw? No one else likes to draw? You've taken an art class. Okay, so one of the things they teach you in art class is perspective. All right? Yeah, so you start with what's called a horizon, and then you have what's called a vanishing point. And so I'll give you a little historical perspective. You've seen caveman drawings? They suck, right? I mean, let's be honest, they suck, right? They had no idea that there was a mathematical foundation. It's hard to draw on a flat sheet of paper and trick your eyeballs into thinking it's three-dimensional, which is the space we live in. To do that, though, to trick your eyeballs, you have to break the rules of Euclidean geometry. So this is a road, okay? I don't know if that road, if you can see that road, but I'll try and help it out by drawing a building next to the road. Do you see that? Okay, I'm tricking your eye to think that that's three-dimensional, even though it's one-dimensional. I mean, two-dimensional, right, on a flat sheet of paper. To do that, I have to violate Euclidean geometry. Because we know that on a road, those lines are parallel, right? They never intersect. But to trick you, I have to make them intersect. Don't I? This is an example of what's called non-Euclidean geometry. This is an example of perspective geometry, totally different. All I'm trying to get at here is that this is a fishbowl of mathematics. It's not the only fishbowl. It's the fishbowl we live in and we like to play in. That's what we do. Everything in college algebra, we're in this fishbowl. But don't believe for any moment that it's the only one out there, the only system. All right? Another property of Euclidean geometry that you're familiar with is that the sum of the angles of a triangle must be what? Take all the angles, 180, right? That works on a flat sheet of paper. It doesn't work on a sphere. You take a ball. If you live on a ball, and you take a triangle on the ball, let's say you take like the North Pole down to the equator. Here's the equator. And then you walk across the equator. You go back up to the North Pole. You've created what we call a triangle on a sphere. And these angles, look, if I take this one, this is a right angle and this is a right angle. That's already 180 right there. So the angle up here is, you're already over 180, guaranteed. So the sum of the angles of a triangle on a sphere does not have to follow the rule of 180. All I'm trying to do right now is make you feel like a piece of sand on in a big beach right now. Just that everything that you know is just a little piece, huh? It depends. We would have to measure it out. We'd have to. Okay. Things are not always as they appear to be. All right, that's the idea. It's not always. Don't ever assume you know everything about something.
It's kind of weird to know that we can solve for dimensions that we can't prove exist.
That's right. That's why there's a lot of very brilliant mathematicians that are blind, because they're not fixated on dimensional space the way we are. So it's very easy for them to work in 10-dimensional space because they're not. They're already having to work in a space that they don't see. Okay. All right. So here's a graph. Let's get through these notes. Here's a graph of x squared. Everyone comfortable with x squared? Yeah. You have inputs and outputs, right? Values go in, values come out. We write them as ordered pairs. Yeah. Anytime we're given the graph of a function, we can run the vertical line test on it to determine whether or not the graph is a function. So there are some examples. Are these functions? Yes or no? So how about part A? Is that a function of x? No. It's a function of x, right? Yeah. Because if I draw vertical lines, I never hit the graph more than one time. Is B a function of x? No, because if I draw, well, that one's okay because I don't hit it at all, and that's okay to not hit it. You just can't ever hit it more than once. So here I hit twice. That's not a function of x. How about C? No. Doesn't look like it. Looks like right there I'd hit it twice, right? Yeah. How about D?
Yes.
Yes, that's a function of x. I only hit it one time, right?
But it wouldn't be a function of y, right? Yes.
Well, a function of y, we would do the test the other way around, which
would be a function of y.
Yeah, which we're not going to look at that. The reason I'm not looking at it is because we are going to do a horizontal line test, but it's going to be testing to see if our function has an inverse. And I don't want us to get confused with the two. Okay, anytime somebody gives you the graph of a function, it is a fountain of information. And we all need to be comfortable looking at the graph of a function and knowing how to get the information out of the graph and put it onto paper. And here's an example of the things that we should be able to determine if someone gives us a graph. We should be able to determine the value of the function at a specific point. We should be able to tell where the graph is positive, above the x-axis, where it's negative, below the x-axis, where it hits the x-axis, where the function hits the y-axis, the domain and the range. So here is a good example. First of all, is that a function?
Yes.
Draw vertical lines. Do you ever hit it more than one time?
No.
I'm hearing yes. Where?
Well, on one, but it's like,
One is not included in either.
Do you see those open circles there?
right,
That means we don't include them. Excuse me? We do not include this. Right, so these open circles mean I don't include them. That means when I draw a vertical line, I don't hit it at all, do I? Here. Anywhere else I'm going to have problems? No. I need to be able to leave that up there. Because I want to ask you all these questions. Maybe what I can do is make this smaller. Yeah, let's just try that right there. All right, everyone, what is f of negative 4?
2.
So what you're doing is you're going out, negative 4, 1, 2, 3, 4, and you're going and figuring out what the y value is, right? So 2? So f of negative 4 is 2. F of negative 1? 1, right? This is pretty straightforward. Where is the function positive? Where is it above the x-axis? So when we say this, we're asking for the x values that you plug in and get positive answers out. So let's take a look over here. If I plug in these x values, am I going to get a positive y value? Yes, up here, right? Up here? In fact, if I plug in any of these x values, I will get y values that are positive. Until I get to where? This right here. This is what, negative 3? What would happen if I plug negative 3 in? Do I get a positive?
you get a negative,
Do I get a negative?
a 0.
I think you get a 0, don't you? So would you agree right now that as long as I'm to the left of negative 3, I'm getting positive values out? Yes? Oh, actually, it stops here. Look, my graph stops right there. See, it doesn't have an arrow?
Right.
Okay, so right there. So far, the graph will be positive from negative 5 to negative 3. Do I include negative 5? Yes? Because at negative 5, I've got a dot up there. Do I include negative 3? No, right? Because at negative 3, what's happening? You're 0. You're not positive, right? 0 is not a positive number. So far, that okay? Is that the only place it's positive?
No.
No. Also, right, like between here and here, it's positive? So maybe
Negative 1.5.
negative 1.5 if we agree. To where? To here, to 0. And I should put parentheses on both of those and put a union here, shouldn't I? Anywhere else it's positive?
Yes.
From 1 to 3.
From 1
But not
Oh,
all.
1
to 3, not including 1, because what's happening at 1?
Yeah, not including
I'm
1
not
or
at,
3. because
there's
the
nothing,
three's
so. So parenthesis 1 to what?
3.
3, do we include 3?
No, because it's 0.
It's 0 at 3, so I don't want to include 3, right? Are y'all following me?
Yeah.
More?
Yep.
After 3, it's positive, isn't it?
So 3.
Forever. 3 to infinity.
Infinity, parentheses on both sides.
There we go. Those are the intervals where my function is positive. Where is the function negative? Well, same story, but you're looking below the x-axis. So negative 3 to 1/2 or 1.5.
Essentially, just take the numbers like the last number, like the second number on one and the first.
You
number
could
on the
you
next.
could possibly, you got to be careful with that though.
No. Like
0 to 1.
Okay, next one would be 0 to 1.
Don't include it.
What if you had a function that came down and walked across the x-axis for a while? Then it wouldn't be negative, would it? And so you wouldn't want to include that piece. Does that make sense?
Yeah.
Okay. Where else?
So don't get used to that.
Yeah, so don't just try and say, oh, I'm just going to take like the opposite of that down here. That's it?
Yep.
Okay. Where's the function 0? In other words, where are the x-intercepts? Those are actual points, aren't they?
We got -3, 0, and 3, 0.
-3, 0, and then -1.5, 0. So you're listing them as points, aren't you?
Oh, yeah.
That's okay. I'm going to list them as just the x values. Is that all right with you? So I'm going to give you the list of x values. -3, where else? -1.5, where else? 0, where else? 3. Now this is a list of numbers, isn't it? This is a list of x values. So I'm going to put a list of numbers in a set of braces. Anytime we have an interval, we use parentheses and brackets. Anytime we have a list of specific numbers, we use a set of braces. By the way, each of these is called a singleton. Singleton. Like a simpleton, yeah, but a singleton. So each one of these is a single value, so these are singletons. See, this right here is not a single value, right? There's infinitely many numbers in here. What is the domain of the function? So that means by looking at this, tell me the x values that you can plug in and cannot plug in. So let's come over here. Can I plug in -10?
No.
No, because there's no function here, right? It actually doesn't start till I get to where?
-5.
-5. Now, as I plug values in and move across this way, do I have outputs? Do I have things coming out? Yes? Have outputs?
All the way to 1.
All the way to 1. At 1, I actually don't have an output. So my domain goes from -5 with the bracket, because can you plug -5 in? Yes, you get an output. All the way till I get to 1 with a parenthesis, because at 1, I don't have anything. And then union from right after 1 all the way to infinity. Good? All right. Got to scroll down here. I should have brought the mouse with me. Can you all smell the skunk? You can't smell it? I'm not getting immune to it. Okay, next question. What is the range of f all the questions on the page? That's it right there. I think I can fit that on there. No, you're all right. Except that I took all the damn... Can you throw me one of those towels, please? Usually the first question on my test for 1414 is a graph that you have to pull all the information off. And it's this information and a lot of other information too. So that's usually the first problem. All right, we've answered everything. What's the range of f? That means what y values come out.
So -1 to infinity.
So if you're looking like left to right and you're saying, do I ever have a y value here? Does my function ever hit? I don't get function until I get to a y value of -1, right? And it does achieve -1, right? Not this way, but this way. So -1 to where?
Infinity.
Keeps going up, 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 up. What about at 2? I have a hole here.
But you have another point.
But I have another point over here, so it's okay. So I am going to achieve 2. And then when I get to 3, it stops, but the arrow implies something, right? The arrow implies that this is going to be going this direction and up forever. So that's implied with the arrow. So the arrow is means a lot. So where did it start again? -1 up to infinity. And remember, these are y values. Everything we've done up to this point has been an x value, hasn't it? Our domains are x values. Our x-intercepts are x values. This, though, is the... So y is 1/2 is a flat horizontal line, isn't it? Y is 1/2 is right here.
Yeah, it says negative.
Oh, sorry, it says -1/2? Yeah, it does say -1/2. Oops, sorry. How many times does it intersect negative 1/2?
Three.
Only 3 times, right? 3 times.
Quite different than
Yeah, we would have had 1/2, it would have been what, 4, 5?
Yep.
Would have been 5.
4. Oh, 5, yeah.
Yeah, 5.
I've done this in high school.
Yeah, this is stuff most of you have seen or done.
Yeah, especially familiar.
For what values does f of x equal 2? F of x equals 2 means, this means what x do you plug in to get 2 to come out?
So whenever y equals 2,
Y is 2. So where is y 2?
4
Happens here at 4 and
negative
negative 4?
the absolute value of 4.
I'm going to write it as a singletons. Negative 4 and 4? Do you see why it's important to put a set of braces around this instead of parentheses?
Yeah.
Because if you, that's the only 2 places it happens, right? Yeah, if you do that, it's going to be everything, and you're saying everything between there, so that's no good. All right. Good? May I erase? Okay. Yes. Oh, I thought you said something. Excuse me. Is that it? That's it for 3-2?
Yes.
Okay. So let's talk about 3-3. Properties of graphs. All right, so we now look at a few properties of functions which will become important to us as you progress through calculus. First of all, what does it mean for a function to be even? So any function is said to be even if this is true. That's what it takes to qualify to be an even function. Graphically, which I'm about to show you, it means this. If I plug in 1, it's going to, into some function, I don't know what function it is, it spits out an answer. Let's say it's right here, right? This is it. According to, if it's an even function, I should get the same value if I plug in what? Negative 1. So if I go to negative 1 and I plug in value, I get the same height, right? See that? And then let's say at 2, it was here. Then that means at negative 2, it's got to be the same height. And it's got to do that for all the points. Which means that if this part over here looked like this part over here would look like this. Understand? Mustache. Yeah, I didn't mean to do that. But that's what it is. It's a reflection over the y-axis. See? So there's an example of an even function. Whatever you get when you plug in x, you get the same thing when you plug in negative x, right? You see the y values correspond. Understand that? Okay. So what we say is that even functions are reflections over the y-axis. We take this, we imagine the y-axis as being this rotational point. We take this and we flip it over, reflect it over, it should go right on top of itself. All right? In the same way, if we bring this one over, it should be on top. Reflections over the y-axis. See, this was me just playing with this. Is this an even function or not?
Yeah.
Yes? So here's that even function living in 3-dimensional space. And here is me rotating it, reflecting it around the y-axis. Boom. Yeah. Okay. Now, that's an even function. What's an odd function? Well, to be odd, it's a little different. So let's see if we can see what an odd function would look like just by the definition. That's the definition for odd. It looks odd. So let's say I plug an x in to this function that's odd. It's going to spit out an answer. That's this, right? Now, make it negative, which would do what to it?
Put it on the negative side?
on the negative side, so opposite side of the x-axis, right? It would come down here, like this. This blue point, right, is this left side. Needs to be equal to what you get when you plug the negative x in. So this was positive x, negative x is over here, right? There should be a blue point, what, over here? Do you agree? Look. Let me try and, this is f of x, right? This is negative f of x. This is f of negative x. So what happens here is this point, right? You plug x into the function. That is equivalent to, when you plug in negative x, it spits it out over here. I don't know if that makes sense. Let me try and do another one. Let's take another point here. I plug it in here. What I basically am going to do is go over the x-axis and then over the y-axis like this. And if I put another point, let's say right here, I'm going to go over the x and then over the y would be here. So let's say that this graph looked like this, right? And this one would look like this. Do you all see that? Now I have another example here in the notes. There's an example of an odd function. Is this just a simple reflection over the x-axis or y-axis? No. It's a double reflection. Okay? So watch. I'm going to make this happen. Here's the graph. I'm going to go in 3D. Here's 3D. So first what I'm going to do is I'm going to rotate it around the x. Hello, where are you? Oh. Rotate it around the y-axis first. That's all it would take to be even, right? But to be odd, you do one more rotation. You now take that and you go around the y-axis. And when you do that, you get the odd function. You see it? It's a reflection over itself twice. Over y, then x. Okay, so you should usually be able to tell if a function is even or odd just by looking at it.
Yeah, so, but we should remember those equations.
Yes, you definitely need to remember those. Because when you get to pre-cal, you'll study sine and cosine. And sine function is an example of an odd function. Let me show you the sine function. This is the sine function. Sine waves look like this. That's the first period of the sine function. And it actually extends backwards like this, okay? And what you can tell here is that if I were to take this picture and let's say flip it over like this, like flip it over the x-axis, it would look like this, right? And then take that blue picture and rotate it around the y-axis, wouldn't it land right on top of that? So that's like a double reflection. Sine is odd. And then after you study sine, you study cosine. The cosine function looks like this. And then on this side, it looks like this. And can you tell that that's just one simple reflection over the y-axis? So remember not only what they look like, okay, geometrically, remember these equations. All right, now we talk about
So basically they're the same thing. Basically.
even and odd.
No, odd.
They're the same thing.
Because when you flip it and then flip it again, it goes the same.
No.
No?
No. Look at it as one side of the, okay, look at this side over here. Okay? Let's say I'm telling you this is an odd function. Then this side of the graph must be this one flipped over and then flipped again, so it would look like this. So now, if I take the whole thing and flip it, it'll be the same picture. Try and take this whole picture, flip it this way, then flip it again over the x-axis. It'll land right on top of itself again.
So even if one flip, odd is two flip.
That's right. Even is one flip over the y-axis. Odd is flip over y, then x. Or you could go flip over x, then y. All right, let's get some of these last definitions in here. A function is said to be increasing on an interval I blah, blah, blah. And there's a bunch of definitions in here. And it can be a little confusing. But the concept of an increasing function, decreasing function, a constant function is easier to see visually. If you were to look at this function and read it like a book left to right, imagine you're on a roller coaster here, you'd be going up, wouldn't you? You'd be moving up. So like if I connect 2 points on this function with an arrow and move those 2 points to the right, the arrow would always point up, wouldn't it?
Yes.
That's what it means for a function to increase. As opposed to decreasing, which means if you have 2 points moving across the function from left to right, if we connect them with an arrow, the arrow is always going to be pointed down. Understand? Yes? And then constant would mean 2 points moving across, connecting with an arrow, and that's always going to be flat, horizontal, the arrow. So increasing function, decreasing, and constant. Let's take a look at this. Let's determine where this function is increasing. I'm going to make it bigger here. And I'm going to go up to the board. And I'm going to take my mouse this time. And let's say that these arrows go forever. Where is this function increasing? So read it from left to right.
Negative infinity to
-2.
So as you're moving across this way, right, we're assuming that this was down forever. So if I'm coming up, right, I'm way down there, and I'm coming up the function. So I'm going up, 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 until I get to where? This point right here, right? Now, I can't tell where that is. Does it look like -1 to you?
-1 to 3.
Looks like, let's just say it's -1. Okay, I don't think it is, but let's just say it is, all right? You okay with that? So we are increasing as long as we are, so F is, how am I going to say increasing? I could write it increasing. You'll see me put an arrow like that. That is the symbol I'll use. F is increasing where? -infinity to -1, right? Now, do I use brackets or do I use parentheses? It turns out that for increasing and decreasing and constant, when you're looking at those things, just always use an open interval. Don't worry about, if you put closed, it's not wrong. If you put open, it's not wrong. They're both right, but sometimes like -1 won't be in the domain, and so you can't close it. So just rule of thumb for me, just always use open. All right, so it's increasing there. Is that the only place it's increasing? No. Looks like here we start going down, 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 and then when we get to the bottom here, we start going up, right? Which looks like, again, is at 1. So that would be union 1 to infinity, right? And if that's the case, then where is it going down? Decreasing. -1 to 1. And that's all, right? So I believe all I have in here is I can show you where it's increasing. It's hard to see it, the dotted lines. Oh, yeah, and it's not 1. Don't worry about this. It's close enough for what we were doing. It's actually -2 over the square root of 3. But you would have never known that, right? That's why you take calculus. Okay? To figure out where this point occurs, you have to take calculus to do it. I think I can actually bring this all together if you just pay attention to this for a second. Look. What was the difference quotient doing? The difference quotient was allowing us to find the slope of a line on the function through any 2 points, right?
correct.
And then we were allowed to bring that other point and slide it closer and closer, right? If I were to look at this point right here, just from your visualization, what do you think the slope of the line at that single point should be?
0?
Think 0? Think it should be flat?
Well, we can't know unless we have a second point to compare it with.
Okay, we don't, but let's say we have a point that's really close to it. This line is not flat, right? But what if that point got a little closer? Would it flatten out?
Yeah.
A little more? And closer? Closer and closer and closer and closer? Yes? Agreed? So would it make sense just theoretically that if it was possible for me to find this slope of that line, that it should be 0?
Yes.
It should be? Eventually, if it could slide close enough. We can't slide it on top of the other one because we get division by 0, difference quotient gave us a workaround, right? So in a calculus class, what you do is you take this function right here, you do the difference quotient on it. When you do the difference quotient on it, you then let h go to 0, and you get some expression. Then you set that expression equal to 0. If you set that expression after the difference quotient equal to 0, you're asking yourself, when is that line on here? 0. And won't that give you the highest point right there? So I'm not going to take you through the difference quotient. But imagine I asked you, do the difference quotient on that, all right? If you did it and simplified it and let h go to 0, you get this, 3x squared minus 4. That's what you would get if you did all the difference quotient, h going to 0, you get that expression right there. If you set that equal to 0, and you move things around, you get 3x squared equals 4. You divide by 3, and you take the square root. Both sides you get plus or minus. Square root top is 2, square root bottom is root 3. And that corresponds to those two x values that I just had a second ago. This right here?
Whenever you're finding the square root of a fraction, you can just individually square root each
Yes.
side.
Yep. So what I'm trying to show you with that is the reason we do the difference quotient is so that we can find the highest point on a graph and the lowest point on the graph. That's why we use difference quotient. That's part of the power of the derivative. In this class right now, what we're doing is we all have to understand what it means, first of all, for a function to be going up and down, because what we're interested in is this point. That point is where the function switches from going up to down, right? This is where it switches from going down to up.
And that quotient will allow you to find that at that point.
At any point, really. The difference quotient will allow me to find the slope of that line at any point on the graph. Is this function ever constant? No? So how would I tell you where it's constant? So I'm going to use a little flat line here. I've had classes before where that's what most of the students seem like they were the whole time. There's flat line. This class, y'all seem like y'all are hanging in there, okay? It's good. So you're saying this doesn't happen, right?
Not in this particular one, no.
So how do you say it doesn't happen?
No solutions?
No solution.
This right here.
0 with a line.
There with a line. That means the empty set or null set. The null set or empty set. This is not the number 0. All right. So let's say I have a basket, right? Here's my basket. Inside that basket, I have the number 1, the number 2, the number 3, right? That basket is not empty, right? It has the number 1, 2, and 3 in it. Now, let me throw the number 0 in there. Now I have 4 things in there, right? 0, 1, 2, and 3. That basket's still not empty. I take everything out but 0. Is the basket empty?
No.
No, I still have a single thing in there, right? 0, so 0's in there. Now I take 0 out.
No, it's empty.
Now it's an empty basket. This is the representation for an empty set. It's the set of nothing. But it's a set. It's a basket that has nothing in it. The number 0 is not an empty basket. The number 0 is it's a point on a number line, or it's a singleton. It's not a set. Make sense? So if you're one of those people who use this for 0, and you're going to do more math, don't ever use that for 0 anymore. Use that for 0. Use that for the empty set. Although the military does use that for 0, I believe,
Yes.
because they don't want you to confuse it with O.
Yep.
So got a little problem there. Oh well. So anytime you have that function, it's increasing. I'm going to move this thing around. I wanted you to see this. I'm increasing, right? So if I were to take a line that would run, remember we're trying to find the slope of a line. If I were to take that line, do you agree that that line right there looks like it would have a positive slope to it?
Yes.
And that's where the function's increasing, right? And as I move this across, watch what happens. When I get to the top, well, right there, that little line, like I just said, should have a slope of 0. Now ignore this. This is calculus stuff. I kind of stole this from my calculus class. But then once I get past that, it's going to start decreasing, right? So now my function is decreasing. Notice that any point on that line, or any point on the curve, if I take it and I look at that line, we call this the tangent line. Notice it's negative slope, right? Where at the middle right here? The function's not constant there because it doesn't flatten out. Like there's not another point that's at the same height. The one right next to it is down. It just looks like it, yeah. Right there we have, so at this point we have a maximum, right? Does everyone understand that? We have a maximum there. We call this a local maximum. Local. Is it the highest point on the entire curve? No, because this goes up forever, right? But locally, this is the king of the mountain. This is the point, this is the shit right here, right? Around here, he's the guy, right? Now, he's not globally the biggest one. The biggest one, there is no biggest one, right? It keeps going forever. Understand? So we call it a local maximum. Over on the other side down here, we have what we call local minimum, which is the lowest point locally, like right there, this is the lowest of the low. But it's not the lowest globally because this goes forever this way. And then in the middle, we have an interesting point. Because notice that our line is flattened out. Do you see that? Just like it was here and here. But that's not a maximum, and it's not a minimum. Right? We will call that in calculus an inflection point. Inflection point.
So is this a negative, or not a negative, is this an odd function?
Is it? I don't know. What do you think?
Looks like it is.
Does that look odd to you? Yeah, it does to me also. If I take this and I reflect it over like this, I'm going to get like this. And then if I flip that over the x, yeah, that looks odd to me. I wouldn't know unless I had the function for sure, but it looks odd.
Although now we can't say that looks odd.
Yeah. Yeah. Because it's ambiguous, right?
Yes. Like, I don't think so.
I think this is probably... I'm trying to get to a point where I can stop, but let's look at this function that actually has points where it stops, right? No arrows that keep going forever. This point right here could be considered to be a local maximum. It is the highest point in this little area, this little region. It's the king of the mountain, but there's not really a mountain, okay? It's a cliff, I guess, but highest point. Over here, this would be considered to be a local minimum, right? It's the lowest point locally, but it's also considered to be, nope, a global minimum or an absolute minimum. This is the lowest point on the entire curve. Understand that? This point right here would be a local maximum and a global maximum. Do you agree? Highest point on the curve? This right here would be local minimum, but not a global minimum, not an absolute minimum. And then this one right here? Local max. So
So a global max or minimum can also be a local.
that's right.
Just to clarify, like a local minimum or a local maximum is simply the lowest or highest point within, like, say, one quadrant. That's pretty much what it is.
You're asking a wonderful question. And here's why.
I had the same idea.
Here's the deal. And this is where things get kind of hairy, okay? Because when we say local, okay, this is the lowest point locally. Your question is, well, how far do you mean locally? Like, how far should we look, right?
Well, basically what I'm asking is, that point right there, that green one, is the lowest point within that one single quadrant.
No, we don't look at it, we don't break it down in quadrant. We look at it as x values coming down, and we say, okay, look, in this little region right here, this little point's the lowest one.
So whenever we're looking for the local minimums or the local maximums, we're looking for either endpoint if we have an any point that the graph changes from going up to going down, or vice versa. Like positive or negative, like increasing or decreasing. Yeah, whenever there's a curve.
A bowl,
Yeah.
okay, this, right? Smile or a frown. Sometimes, not always. You can have what's called a cusp. And then that would be a local
Well,
maximum.
that's why I didn't particularly word it like that. That's why I said whenever it changes from increasing to decreasing or vice versa.
Okay, so if you change from increasing to decreasing, it doesn't necessarily mean that you have a maximum either. And I can show you an example of that, which would be, imagine a function that has an asymptote, which we really haven't talked about too much yet, which goes like this, and then on this side it goes like this. And it goes from increasing to decreasing, but it doesn't have a max because it blows up at that point. We're out of time, but I'm going to address this question because it's a wonderful question. In mathematics, to say that you're locally or near, use the word near, that's a very bad word in mathematics because what do we mean by near? Like, am I near SeaWorld?
Relatively.
Relatively, like compared to the distance between me and my camera, I'm near, but SeaWorld is far compared to my camera, right? The sun is far, isn't it?
Yeah. It's closer.
But it's close compared to Pluto or some Alpha Centauri, the next nearest star. So it's all relative. So we wave our hands. If you become a math major, you have to nail that definition down a little bit better. All right, try and do your homework. See how it goes. If you have any questions, bring them to class next time.
Like if we also have some problems, we can still visit you on the office time.
Yes, yes, absolutely. Did I do the sign-in sheet again?
Yes, we forgot to do that.
Golly. Do you want me to call it or just let you sign?